If I asked you if you believe that gravity exists, I doubt there's anyone in the room right now that would say no. Gravity is a part of our life. It's been a part of your life since the day you've been born. It always affects you. But the interesting thing is nobody really understands how gravity works. And so it's an interesting force. It's a long-distance, non-contact force that is very, very difficult, if not impossible, to explain. And we're going to, because of that, we're really only going to talk about describing gravity today. However, even as we describe it, I think you're going to see that there's a few things about gravity that you didn't know before. So let's just go ahead and start and jump right into it. Go ahead and write down, this is what Newton's law of universal gravitation is. It describes the attraction between two bodies due to the force of gravity between them. So go ahead and pause the video now, write that down in your notes, and then hit play when you're done. So I want you to see that there's two things in this definition of gravitation that most people don't really realize. So if I ask people, what is gravity? If I was to ask you, what is gravity? Many people will say something along the lines of, it's the force that pulls us down toward the earth. And that's not untrue, but it's not completely true either, because gravity is not just limited to planets, right? It is universal. Gravity is universal, which means it's everywhere. It's on this planet, it's on the moon, it's gravity from the sun, it's all over the universe. But not only universal in terms of all over the universe, it's universal in terms of, it describes the attraction between two bodies due to the force of gravity between them. Every object puts a gravitational force on every other object. So it's universal in the sense that there's no object in the universe that is not included in this description. Every mass puts a gravitational attraction on every other mass. So if you're in class, you're sitting next to someone, and I want you to be honest about this question. Are you attracted to that person? I mean, look at them right now, look them in the eyes. Don't be creepy about it. Don't be creepy about it, but just like ask yourself, am I attracted to this person? Okay, so clearly I'm not talking about the romantic kind of attraction. I'm talking about a gravitational attraction, because you are attracted to that person and they're attracted to you. But it's the force of gravity. It's a gravitational attraction. Every mass, every object with mass puts a gravitational force on every single other object. So it is universal. Everything has gravity. And you ask the question, well, if I have a gravitational force from the person sitting next to me, why can't I feel it? And the answer is, our mass isn't enough to make the force very big. We're going to find out soon that the force of gravity is actually a pretty small force. So you need a really, really big mass to make it show up, like a mass the size of the Earth or the Moon. But nevertheless, there is a force of gravity from every single object. So the force of gravity is universal. Everywhere in the universe, in space. Many people think, oh, there's no gravity in space. If I ask, is there gravity in space? Many people say no. We've talked about that before in this class. We've talked about why the astronauts feel as if they're weightless on the International Space Station. It's not because there's no gravity, it's because they're actually in constant free fall. There's almost as much gravity there as there is here. So there's gravity everywhere. You actually can't get away from it, and it's due to every mass in the universe. The other thing that many people don't realize about gravitation is this. We already said this, every mass attracts every other mass by a force, but objects want to be pulled toward each other, which is a little bit counter to what most people say, which is that the Earth pulls us down. That seems to indicate that gravity is a single direction force, is a unidirectional force. In other words, the Earth only pulls on me. Well, the reality is the force points along an imaginary line connecting the two masses. So let's just say we have the Earth and the Moon. The reality is the Earth does feel a gravitational pull from the Sun, and we know that because the Earth is revolving around the Sun, right? Because of the Sun's gravity. But it's also true that the Sun feels a gravitational pull from the Earth. Right? And you can put any two objects here, you and the person next to you, the Earth and the Moon, whatever it is, they both pull on each other. The Sun is pulling on the Earth is pulling on the Sun. The Earth is pulling on the Moon is pulling on the Earth. They both exert a gravitational force on each other. And it's interesting, there's a lot of effects of that we can talk about that are interesting, but for now I just need you to know that it's a two-directional force, that gravity is from each object. Now, since we know that gravity is due to each object pulling on each other, there's an interesting question that comes up, and the question is this: which of those forces is greater? Is it your gravitational pull on the Earth or the Earth's pull on you? So you know that the Earth is pulling you down. That's obvious. We've drawn the force of gravity on free body diagrams for several weeks now. We know that the Earth pulls on us. What we didn't know before is that you're also pulling upward on the Earth. And the question is, which of those two forces is greater? Is it the Earth pulling down on you, or is it you pulling up on the Earth? Many people will say that, well, the Earth pulling on me it has to be much, much greater because the Earth is so much bigger. Since the Earth has so much more mass, that force has to be greater, right? Well, the answer is they're actually the same. Both of those forces have the same magnitude. The Earth is pulling on you with the force of gravity. You are pulling upward on the Earth with the exact same amount of force. And a lot of people have a hard time understanding that. How can that be? How can that be that the Earth can pull on me the same amount as I'm pulling on the Earth? Well, the answer comes in the equation for gravity that we're going to get to in just a minute, which is that the force of gravity is really due to the product of both masses that are pulling on each other. In other words, it's not one or the other that governs the force of gravity. It's the product of both of them. It's our masses multiplied together. So if you do the Earth's mass times your mass, and then you do your mass times the Earth's mass, it's the same number. It's the same force going both directions. Not to mention the fact that Newton's third law states that the forces any two objects exert on each other have to be equal. The Earth pulls down on you. The Earth is object A, you're object B. Object A exerts a force on object B, but object B also exerts an equal and opposite force back on object A. So the two forces, according to Newton's third law, have to be equal. But they don't look equal. They don't seem like they're equal because, I don't know about you, but I've never jumped up and experienced the Earth coming up to hit me. I've never pulled the Earth toward myself. Why doesn't it seem like those two forces are equal? Well, the answer is it's Newton's second law. So we know that the acceleration that results from that equal force is drastically different. Clearly, you are the one that's accelerating from this force. If you jump up, you accelerate back down toward the Earth at a rate of negative 9.8 meters per second squared. There's no way you're ever going to pull the Earth toward you, even though you're pulling on the Earth with the same force. And the difference in acceleration is explained by the difference in mass. That's Newton's second law. The object with less mass gets greater acceleration, and the object with greater mass gets the smaller acceleration. So the Earth has a much higher mass, and when I say the Earth has a much higher mass, it's silly to even say that. Like, the Earth has such a greater mass than you, it's not even worth comparing. So I want to do an experiment right now to illustrate this. I have a slinky, and on one end is a tennis ball, and the other end is a baseball. So all I'm going to do is simply put these on either end, and I'm going to let them go. And predict in your mind what's going to happen when I let them go. Most people say the balls are going to meet in the middle, which seems to make sense, but let's see what happens. Ready? 1, 2, 3. And we get the baseball falling off the table. But that's clearly not what happens. The balls don't meet in the middle. The tennis ball seems to move toward the baseball, and the baseball hardly moves at all. And so the question is, why does that happen? Why does the tennis ball accelerate more than the baseball does? And many people, when they start to think about this, they say, well, the tennis ball must have had more force exerted on it. It must have had a stronger force pulling it that direction. That's the reason why it goes farther, because the baseball can exert more force. The answer is no. Many people say, well, the tennis ball moves farther because the baseball can't move. No, it can move. It can move just fine. I'm exerting enough force to make the baseball move. It can move. The forces on each of these are the same. It's the slinky that's providing the force. The slinky pulls on the tennis ball. The slinky's also pulling on the baseball. Newton's third law says those two forces have to be the same. The reason for the difference in their acceleration is the difference in their mass. The one that has less mass has the greater acceleration, but the one that has greater mass has the smaller acceleration. And the interesting thing is, if this is a metaphor for the Earth and you, the baseball would be the Earth, and this would be you. But we really can't do this if this is going to really make sense. So if this really is you, if this is your actual mass, we would need something heavier on this end to approximate the difference in mass between you and the Earth. And I ask my students a lot of times, what do we need to put on this end to make it be just as different as the mass between you and the Earth? And many people will say, put a bowling ball over there, put a truck over there, put a building. You actually would need the moon on this side. Like the actual moon, as big and as massive as it is right now, that's what you need. You need the moon over here. So picture the moon, I'm holding the moon and the tennis ball. And then I dare you to stretch out the slinky and let them go. The moon's not going to move 1 inch, not a bit. And it's not because it's not free to move. It's because the mass is so much greater that the acceleration is basically zero because it has such a big mass. It has such a big mass. And when we put our mass into the equation, the product of our two masses is so ridiculously small. It's almost as if there's no gravitational force. There is, but the only object that's going to move because of that small force is us, because we have such a small mass. Okay, so let's keep talking about the force of gravity. Let's move on in the notes and talk about the gravitational constant. So basically, when Newton formulated his theory of universal gravitation, it was really interesting how he did it, because he was looking at orbits of planets, and he figured out, and this is pretty phenomenal, he figured out that gravity had to be based on the mass of the objects involved, and it also had to be based on the distance between them. It was indirectly related to the distance and directly related to the product of the mass. But he found out that there had to be a number in that equation that made all of his numbers work out, and we usually call that a constant in science. His number, the gravitational constant, is what he discovered, and he called it, not surprisingly, the universal gravitational constant. And it has a value of 6.67 times 10 to the negative 11. There's some units for it, but you don't need to know that. The most important thing that you really need to know here is that this is a really, really small number. It's like a 667 with 10 zeros behind a decimal. It's a really small number. And that gives us an idea of really how weak the force of gravity is. How weak the force of gravity is. Again, it takes a mass the size of the moon, or somewhat less, but a large mass, the size of a large planetary body, to really feel the force of gravity. We can't even hope to feel the force of gravity between us because our mass is so ridiculously small that this force between us is so incredibly weak.